suggest we get started again. Josh is ready. I've got two announcements. The first one is that we still have some free TTK goodies, so please make sure to grab a t-shirt. The second announcement is that if you have questions during the presentation, that would probably be preferred if you could enter them in Slido, such that then one of us can repeat the questions afterwards with the microphone and get to the attendees who are watching remotely. Otherwise, they will not hear the questions. So if you have questions, that'd be much better to type them in Slido. Thank you very much. And with this, I guess we can get going with Josh from University of Arizona to get a tour of TTK. Thank you, Josh.
All right. Thanks, Julian, for the introduction. Are we okay in the back with sound? Good. All right. So my name is Josh Levine. I'm faculty at University of Arizona, and my job for the next 25 minutes or so is to give you all a quick tour of the topology toolkit. So I'm going to talk a little bit about some of the background on the software engineering. I'm going to talk and show you a little bit of demos, and then try to translate some of the technical content that we've been seeing, for example, with Bei Wang's talk, into some of the things that are actually practical filters in TTK. So it's a real pleasure to be here. Let's start with a little bit of history. So TTK has actually now been around for, I guess if I'm doing math here, over 5 years. The public release was in 2017. It was about 100,000 lines of C++ code, and it's been growing ever since with a huge user base. My list here of collaborating institutions I think is actually already a little bit out of date. So there's 12 different universities, 3 different companies. We've had quite a lot of people contribute to this public software release. We're very excited about that being kind of a community focal point. And at this point, hopefully, you kind of have a feel for what TTK is all about. It's good for basically doing topological data analysis on low-dimensional scalar field data. And this is the type of data that can come from scientific and engineering applications. A lot of different data sets from astrophysics, biological imaging, quantum chemistry. We can all take these and model them as scalar fields in different ways. It doesn't have features for everything yet. A lot of topological analysis you see now is on different modalities of data, like vector and tensor field data, and high-dimensional data as well. These features are not the primary base of TTK, but I say this with a little bit of an asterisk next to it, because we've added a bunch of different features in there that either map these sorts of data into scalar fields by conducting or computing scalar fields of interest from something like a vector field, or allow you to work with things like point clouds that you could model with a high-dimensional data set. There's tons of online resources for TTK. If you haven't yet gone to the website, I missed the first few minutes of the workshop, so I put it back up here just in case for people to see. But if you go to topology-tool-kit.github.io, you can find all sorts of examples online, installation instructions. If you're following along on your laptops today, I recommend pulling up this web page and starting to work on this. I also want to take the opportunity to mention our mailing list, the TTK users at googlegroups.com. This is a great resource to connect with the TTK developer and user community. Generally speaking, if you email this, we reply within about a day. Someone will pick up the email and try to answer your questions along the way. So we've shown you a little bit in the earlier parts of the workshop, some of the mathematical things. We've also shown you some of the computational tools underneath it. TTK underneath is being powered by tools like VTK and ParaView, and also tools like Docker and so forth that you can see to help you do the installation. This is really the back end of TTK that we're trying to release publicly for end users who are just interested in doing topological data analysis. You should be able to download ParaView. These days it's now released with ParaView. You get the TTK filters built in, and you can use that as a nice visual interaction for working with topological data analysis. I'll demo this in just a few minutes. Behind the scenes, though, there's other ways to talk to TTK as well, too. There's a pretty lightweight Python API that you can work with as well, and you can also work with the in vivo environment as well. If you're a developer, though, and you're interested in contributing to TTK, there's a variety of different ways you can make touch points with the software library as well, too. You can code things directly in VTK, you can code things in pure C++, or you can work with TTK and Python if you want to kind of get up and running quickly. On the very, very advanced end, you can actually work with TTK independent of all of these things. You can just write pure C++ and talk directly with TTK. I'm going to breeze through this ParaView slide quickly. Charles already gave a great demo of how ParaView works, but ParaView is really being used here to leverage for all the things that we didn't want to reinvent the wheel for. So all the rich rendering APIs, things like OpenGL and Osprey, if you want to do rendering of data, we get that for free with ParaView. The other thing that we get that's really great for ParaView is a rich I/O support. This allows us to open and load data sets of all sorts of different formats, and then it's really easy to convert them into the TTK scalar field format. There's an interesting pipeline interface. You'll see lots of demos of this for the rest of the day, where people are trying to do interaction between running filters as blocks, and they do this kind of visual programming methodology. This is something that was built into ParaView from the get-go, from the design side. So kind of summing that up a little bit in terms of how that user experience works, I'm going to show you a little bit of this visually in terms of just a couple screenshots of this. If you're running a standard TTK pipeline, it might look something like this in ParaView, where basically on the left, you've designed a complex pipeline. You get visual things in their windows that are showing you the data sets that you're analyzing, and then you got other statistical tools. And you can interact with this in kind of a nice hybrid interface where you're working with multiple views and interacting on all of this. What you're seeing here is a persistence diagram, a persistence curve, and then the more smell complex doing this analysis of this data set. If, though, you wanted to work with it in different ways, you can basically emulate this outside of the ParaView environment. So for example, you could do a standalone visualization of that same data set doing the analysis here. This would be a standalone program you would write, run from the command line, and it'll actually just pop up a window and show you the analysis underneath. You can then be running this as scripts, and you'll see here that this little widget that I showed up here is showing you kind of the console line that you get where you're doing all of the analysis on the back end. And then here you can see kind of the different ways you'd write this with respect to code. If you want to do this in a really lightweight way, you can just use a Python API. So this same script that you're looking at here was 21 lines of Python code. Here's what happens as you increase complexity. If you're working with VTK and C++, you're now doing it maybe with twice as many lines of code. And then if you're doing the more verbose, pure C++ version of this, you're trading complexity for flexibility in some sense, and the pure C++ developing version of this is now 100 lines of code. So it's all equivalent ways to interact and work with the TTK modules and the API, producing similar analyses at different granularities. Whatever you want to customize for, we kind of have tried to design this with access points for all of that. So with that, I'm going to do a quick demo. This demo has, forgot one link on the slides. If you want to check out some of these examples, there's a couple different example pages on the website. Here's one of the links to download and check out this specific example that I just showed you here. All right, now with that, I'm going to switch and show you a little bit of a live demo of doing analysis. I'm going to do this from scratch because what I want to do is actually recreate for you an experience that I think at least one person in this room has seen before, which is an experience from when I was teaching using TTK. Essentially what happened was we were doing analysis using a data set from Herbert Adelsberner and John Herer's textbook, where we were going through and they were looking at analysis of Morse-Mel complex of microscopy data. And I'm actually going to recreate that analysis for you here. The conversation went like this in the classroom. We were reading the book and going through the section, and I said, you know what, I bet we can do this live in class. We went with our computers, we found the data set, it was publicly available, we downloaded the data set, loaded it up in ParaView, and recreated what I'm going to show you now in the next, hopefully, 5 minutes. So give me 1 sec, I'm just going to switch here. All right. Mirror. Cool, all right. So now you all see what I'm seeing here. And this data set was in the Herbert Adelsberner's book, and basically we just found the reference for it, the citation, downloaded it. I've done a little bit of conversion. Here you'll see this microscopy.vti. This is this microscopy data set stored in the VTK image format, the VTI format. And here I'll load it up and you can see what we're looking at. And this is actually a slice of basically the cellular structure of fruit flies along the way. And if you're looking at this just with standard viz tools, you can actually see these kind of cellular structures in here. The problem, of course, is there isn't like a specific threshold I can get. I can't say, give me the numbers at, for example, 180 to get the boundaries of all the cell walls. This is exactly the sort of thing that topological data analysis helps shine with. So let me show you a little bit of how that analysis might work. Just if I said, well, let's, for example, look at a cellular decomposition from something like the Morse-Mel complex. And if I just add that in, I'll do that in a couple quick filters. So here I'll first tetrahedralize. And here all I'm doing is modifying the data so it's a triangle mesh to fit in the simplicial complex format. And here I'm just going to code the Morse-Mel complex or run it as the filter. So you see I've added this TTK Morse-Mel complex. All these white lines and arcs that you're seeing here are the decomposition from this raw data set. Of course, the data set's noisy, has all sorts of things in here, and the cellular structure you don't really see well, although if I zoom in, and here we'll zoom in, you can see that there are some lines on the arcs of the Morse-Mel complex that are actually following the subdivisions of the cells. What we have here is we have a problem with noise. Here's where the persistence diagram can help filter this out. So I'm going to remove this one. I'll split my view for everyone so we can look at the persistence diagram side by side. And so now here I've added a TTK persistence diagram filter. And you compute that, and what you see on this right is something like that barcode that Bei Wang was talking about. Each of these vertical lines that you're seeing is one persistent pair that we're looking at in the structure. And from here, I can use this tool as basically an engine to do the simplification of this data set. I'll pick various thresholds of what I want to preserve in the persistence diagram, run a topological simplification filter, and then take a look at the more small complex. This requires a couple filters to add, so I'll add them one at a time. So first of all, what I'm going to do is use a threshold filter. This is the standard pair view threshold filter, nothing special that we've coded here. And here, I'm going to threshold on the persistence values directly. So when we build the filter for TTK, this computes for each pair, stores the persistence threshold associated with each of them. And you can kind of see, hopefully, the range here goes from 0 to 500. These are talking about the range of bounds on the pairs. If I want to preserve the ones that are high persistence, I'll basically chop away from the bottom. So I'll increase the lower threshold. So let's say I want to remove the bottom 10%, something like that. And you can see on the right, I filtered and removed some of those cellular structures. I'm only keeping some of those features around. Back here on the left window, where I'm looking at the actual data set, I can now use this as a tool to filter the topology directly. I'll do this with two steps. First, I'll do a topological simplification filter. That's going to take as input the output of the data set itself. So here's topological simplification. And then I'm also going to add in a set of constraints from the threshold directly. So now on the left, I've reloaded, and you do see the scalar field changed it a little bit. I directly simplified the scalar field associated with it. I may have been a little aggressive and removed too many features, but you can see already the filter adjusted a little bit. And now what I'll do is I'll recompute that more small complex directly on this simplified data set. So now you can see I have a different set of arcs that I'm looking at along the way, and I can filter these to get just the subset of arcs associated with the boundaries. So for doing this, what I'm going to do is actually only look at, I believe it's the ascending. And now these ascending arcs, hopefully you can see these thin white lines. I'll make them a little bit thicker for you, though. We'll go here. So these white lines here are now the boundaries of the arcs that I'm pulling out. And this is kind of not a coincidence. What we're getting here are these lines that are associated with the boundaries of each of these cells. They actually correspond directly to the biological entity that we're looking for too. But I did simplify too much, so let me go back and adjust that threshold. Here what I'll do is I'll go back to the threshold filter, and I'll simplify a little less. Let's maybe keep around the bottom 4 or 5%. Now I have actually a pretty good capturing of all those cell walls. The cool part about this, I didn't time myself, but that was 5 minutes. I didn't really have to think that hard. I had to play with one number, and I got this analysis in a great way. And it has all the extra features built into pair view. So for example, what I didn't show you, I was only showing you the boundaries. Let's look at the segmentation directly. So here what I'll do is I'll turn over here, the segmentation, and we'll switch to how we're coloring it, so we're actually looking at the descending manifolds. And you see here now I've actually able to color out and associate each of the individual regions there. Pretty cool. And at the time, like this was, I think 2017 when I was doing this, or 2018 in the class, we were all pretty impressed with ourselves that we were able to do topology on the fly. Now I look at this, I'm like, oh yeah, everyone should be able to do this. And that's kind of why we're running these tutorials, so that you all can do this at home just as easily as we did. All right. So let me switch back to my slides. Cool. All right, so what I'm going to do for the rest of my allotted time is I'm going to give you a quick tour of all the features that you talked about. You'll see what we're going to do is there's kind of a one-to-one mapping. The object that we've talked about that's a mathematical object, we've implemented as a filter in TTK, and you can kind of interact between. I won't do any more live demos, but I'll show you a couple images along the way of how these actually look when you're using them in analysis pipelines. It's worthwhile to start out quickly, though, and talk about the data modality that we're working with as well. We're basically modeling all of our scalar fields as PL, or piecewise linear scalar fields. So again, we still have functions on some manifold where at every point we have some scalar value. But here, what I'm really being specific about is the manifold itself. I'm calling the manifold here a simplicial complex, a collection of triangles and tetrahedra, simplices along the way that store and encode each small subregion of the data set itself. And for each of those, we have these values that are stored on the vertices of the individual corners of those tetrahedra and the triangles along the way. That gives us enough information to interpolate the data in the inside using linear interpolation, hence the name piecewise for each tetrahedra and linear, the linear interpolation along the way. What's cool about TTK is we actually have a lot of different vehicles for working with data and kind of forcing it into a piecewise linear modality. So for example, you saw me use the tetrahedralized filter. Another option is to use what we call an implicit triangulation, which takes something on a regular grid and actually just maps it directly to a tetrahedralization or a triangulation of the data set. This covers actually a pretty good set of common formats. We also have some extra features that have come in and actually have been modified recently to include things like periodic boundary conditions and really map the data to more than just a block of space, but actually try to map and match what's in simulations and medical images and so forth. So once we load a data set that's in this format, we can do a variety of different things with it using a collection of topological features. I'll quickly go through a few of those and kind of give you a whirlwind tour of some of these along the way. You've already seen a couple of these things, but some of these are actually a little bit new because I didn't demo. You saw, for example, in Bei Wang's talk, well, it's interesting to look at the individual critical points, the extrema associated with a scalar value, or scalar field. This is pretty straightforward to do in TTK. We run our scalar field critical points filter. This produces a point cloud where we've labeled the point cloud of different critical point types. You see here in this image, maxima are these green spheres, minima are the blue spheres, and saddle type critical points are the white spheres going through. The algorithm's actually really trivial to implement. It's a linear time algorithm. We go through each simplex or each vertex one at a time, and we just detect locally, are you a critical point or not? So this is nice, kind of fast, straightforward to do, but it gives you already a working tool that tells you a very high-level summary of the data along the way. One thing I want to point out, though, with respect to this is sensitive to noise, and this is where topological simplification, like I just showed you, really comes in and helps out. I've taken that scalar field, and now it looks a little bit bumpy and fuzzy. I've added a little bit of noise to the scalar field. And if I recompute the critical points, you see we create a number of spurious critical points, all those green and white spheres that appeared in the corners of that 2D scalar field that we're looking at. And you can see here what's cool is we can use the persistence diagram to disambiguate those features. So we've implemented, I showed you the persistence diagram filter, and I'll talk in a second about the persistence curve filter as well too. This detects for us all extremum saddle pairs. It's using a linear rhythmic time algorithm that's been efficiently parallelized. My poor little MacBook can't do all the parallelization, but if you're running on a desktop machine, that's no problem at all. And what we're doing here is we're connecting up saddle and extrema pairs and then showing them in the diagram on the bottom right. We can also do saddle-saddle pairs. That requires a little bit of extra computation to get as well too. When I add noise in, though, that's reflected in the persistence diagram. So you're seeing all those additional pairs that are low persistence. They're on the diagonal. They don't have a strong difference between when the pair was born and when the pair was merged together. If I increase noise, you'll see that those critical points actually bump up and they get further and further away from the diagonal. In extreme case, I've added lots and lots of noise to this data set, created lots and lots of critical points, and now that's reflected in the persistence diagram. So what we can do is we can use topological persistence and topological simplification together to detect and preserve topological features, just like what I did in my quick demo. A question you might ask, though, is, well, how do I know how to set that threshold? I didn't have time to demo it, but what we have here is this notion of a persistence curve that gives you a statistical summary of how many critical points, that's the y-axis here, are at various different thresholds of persistence values. And what we typically do here is we look for knees in this curve, places where there's stable regimes of a certain number of critical points that are persisting for a long period of time. We can use that to select a threshold, and then what we can do is merge that all together in this topological simplification filter. This is a paper that was actually now a decade old from Tierney and Piscucci that does a linear pass through the entire data set, given a set of constraints, and it preserves those constraints along the way. And what this actually does is it's doing something like a peak chopping algorithm. So if I preserve a certain set of features, you'll see, well, I wanted to preserve just the two big mountains in this data set. I did this by chopping off the top mountain. So that's where you saw the scalar field change a little bit. I was showing you just as colors, but here you're seeing with elevation the same phenomenon happening. And I can continue to remove. It's actually a neat algorithm because you can just select which features you want. It's not just driven by a threshold. It's basically saying preserve a set of pairs. So I can remove big maxima, small maxima, and so forth. In addition to all of this, what we can do is we can actually take those features and we can use them as a way to rebuild the data set directly in a way that allows us the data set to be more compact. And this allows us to do what I would call topologically aware compression. And here you're seeing an example of how that works. So if we start out with a high resolution data set, this again is a toy data set, but it's 2.3 megabytes of data along the way. I can say, given a set of critical points that I want to preserve or features I want to preserve, use the persistence diagram, select them, and then do a compression algorithm along the way. What this compression algorithm does is allows me to shrink the amount of data that I'm storing while still having a data set that preserves the same set of features. And here you're seeing that compressed image along the way in the bottom. And I can play around with that a little bit. This is an algorithm from Solar et al. And Pacific Viz 2018. And as I start to simplify, what I'm actually doing is I'm flattening off the data and then compressing what's left over along the way. So you can see here I chopped off the mountain, and I'm kind of storing it in these kind of plateaus along the way. And I can do even more compression along the way, or on the real extreme side of compression, I preserve something with equivalent topology, 3 cylinders that are corresponding with the 3 noisy mountains, but I'm able to store the data in a much more compact way. Of course, you might look at this and you say, well, this wasn't really the data set. It has, I guess, the same topology as the data set, but it certainly geometrically doesn't look quite close. One of the cool things about this is we can mix topology and geometric features together. So here's a similarly compressed, although it's a little bit larger data set now, where we've also put in a constraint to basically satisfy being geometrically close to the original data set as well. And this is a nice trade-off. You can kind of pick and choose between how much compression you want, which features you want to preserve, and how geometrically close to the original data set you'd like to be. We can also play around with this in different ways, integrating with, for example, the ZFP compression algorithm. This is a really popular compression algorithm that's out there for doing lossy compression of the data set. And we can kind of pick and choose what granularity we want to preserve and then talk with ZFP as well, too. Okay, I have a few more minutes, so I'm going to talk now about a few of the higher level summaries that we've talked about in TTK in the past. The one that we've mentioned already in this conference is something called the merge or contour trees. And here what we do is we build this algorithm using the module that's called FTM tree. This uses gives us a summary of all the level set segmentation of the data set. So for example, we go from our 3 mountain ranges to now this tree-like structure here. I'm showing this data structure for you for all the maxima of the data set. And it's giving you this kind of structure summary of not just how big the features are, but which features are adjacent to each other. The algorithm we do here is actually really neat. There's been lots of different parallelization for it. Charles, who was presenting a little bit earlier, the paper that's implemented here is actually, he was one of the authors of working on this algorithm as well. The thing I want to highlight, though, is not that we can compute the merge tree, but all of the features that you get from TTK that are built into the merge tree. So what you're seeing here is, okay, I showed you the skeleton, but for each arc in that skeleton, I've actually mapped them to segments of the data underneath the hood. And there's this one-to-one mapping between the raw data itself and the individual arcs, which allows me to do things like segment the data set as well, too. Here now I'm able to preserve each of those mountaintops that are associated with the leaf trees in the merge tree structure. And of course, these things can be integrated with all of our other tools like topological simplification. I kind of demoed that for you as well, too. So here's showing you with noise and then preserving those same sorts of features along the way. What does this look like if you actually put it on real data? Here's an application here where we showed you this for biomedical imaging. This is a CT scan of a foot that we're looking at, and you can see the bone structure of the foot as well, too. Well, those show up as 3-dimensional peaks and valleys in the volumetric data set. And what we're looking at here is actually, after some persistent simplification, we preserve the 5 biggest features and the merge tree associated with the 5 biggest features in the data set. And lo and behold, those actually correspond to the 5 bones associated with the 5 digits of your foot along the way. And this is actually pretty nice. It's a little bit coincidental. We got lucky with the data set because biomedical images can have sometimes complex noise that messes us up a little. But for here, it worked out quite well. They were able to map directly the data to the merge tree structure. We can do this at one other fine granularity. So what if I say preserve the top 10 features in the data set? And here actually you can see now I've recolored all the feet to correspond with actually not just the digit, but where the digit separates at each knuckle along the way. So those merge tree structures actually do map into a skeleton, in this case, a real skeleton of a real data set along the way. I'll quickly mention the regraph as well, too. If you're not working with simply connected data, the contour tree or merge tree structure maps into something called the regraph that has to maintain loops. Our algorithm that we've implemented here still does a level set segmentation here, but accounts for the loops along the way. And the data structure that comes out of it, the regraph, acts equivalently to how the contour tree works. We have all the same metadata associated with it as well. And then one final structure I'm going to talk about in brief is something called the Morse-Smell complex. I showed you this for my demo when I was working with the cellular data. Here what we're doing is we have a module called the Morse-Smell complex, and what this does is it uses discrete Morse theory to map and extract the Morse-Smell complex. Here it's the arcs and the segmentations that I demoed before. There's a couple cool features of this, though. One is the fact that we have a discrete grading computation that maps and is corresponding to or consistent with the piecewise linear interpolant. This was some work that we originally started with earlier implementations, but the final version of this is something that Tierney et al. Worked on in 2017 based on, I think it was Vanessa Robbins' algorithm in the end, but the original algorithm was one based on, I think I have it in my notes, just so I can get it correct. Yeah, it's from VJ's group as well, too. Yeah, but now it's the Robbins algorithm. So we've modified this and optimized it as well too. And again, like the other filters, it works and it tolerates noise just like what I demoed. I'm going to show you one other quick demo just to kind of stay on track with time though. Here's an example from quantum chemistry. We're working in 3D data and we have an electron density data set that's coming out of here. And here what you're seeing is a level set contour at a particular region, which kind of corresponds to the blobby model you might expect for this particular molecule that we're looking at. It turns out that the Morse-Mel complex actually has a nice relationship with this as well too. If we start to extract the minima and connect them up with arcs of the Morse-Mel complex, a carefully selected subset of those arcs, this actually corresponds to something like the ball and stick model you might remember from your chemistry classes. And we can go a little bit further and do the segmentation to actually help to separate and isolate out each of the individual atoms in this molecule as well. So in at least for sake of time, I'm going to kind of wrap it up here quickly. I really only showed you, just to kind of talk a little bit about what I didn't cover, I really only showed you the big major features here. The rest of the talks for the rest of the session are going to actually get into nitty-gritty of individual, more advanced features as well too. But at this time, I'm happy to take any questions that people have, since we have, I think, a minute or two for those. Yeah, thanks,
right,
everyone.
I think we can thank Josh for this great tour. If you have some questions, either enter them in Slido or you can ask them now. It's just that I have to repeat them in the microphone to make sure that
I'll
the
repeat them
attendees.
too.
Yeah.
Yeah.
So you can also just ask your question right now, and we just need to repeat them in the microphone.
Anything on Slido?
I have a question for you, Josh.
Oh, okay. Question.
Can TTK only do scalar data?
No, of course not. TTK can do plenty of other things beyond scalar data. A lot of this, though, it falls, I would say, into one of two modes. One is taking an input data set and converting it to a scalar field, right? So you can do something like take a vector field and compute its magnitude. Second is you work with a point cloud, and there are operations to work directly with a point cloud where you build a simplicial complex on top of the point cloud. That's another thing to do. And then third and final, we've been starting to work on actually implementing vector field data as well, too. So various modules that actually pay attention to vector values and do things that are related to topology. Did I miss anything, Julia?
That was great.
Thanks.
So if we don't have any more questions, I think we can thank Josh again.
Yeah, thanks everyone.
And move on to the next presentations by Federico Juricic from Clemson University.
Of course. It's actually that.
All right. Hello, everyone. I'm Federico Juricic, an assistant professor at Clemson University. And today I'm going to mention to you one of the new features of TTK, which is the compact triangulation. So to give you a quick idea of why you should care about the compact triangulation and what this is about, in general, if you think about the type of data that you can handle, we are always thinking either to volumetric data, so something that is distributed on a regular grid, or some type of simplicial mesh. And if you are familiar with geometric data processing, you already know that if you're dealing with a volumetric data, the actual overhead of after loading your data set of computing the connectivity relation there is almost null. So that means practically if you have enough memory to load the data, you also have enough memory to compute the connectivity relationship and eventually run your TTK plugin of choice. With simplicial meshes in general, that is not true. So even after you loaded your mesh, if you want to, depending on the connectivity information of how triangles, tetrahedra, and edges are connected, depending on what you need for your plugin, you will need maybe significantly amount of memory on the top of that. So the compact triangulation is meant to kind of solve that issue. To just give you an idea of how TTK works underneath, every time you load a mesh and you run a plugin, what happens at first is that TTK will compute the connectivity information for your mesh as the first thing. After that, the TTK plugin will get the green light, which means you can actually run the topological algorithm now, and after that you will get your output visualization, right? So what may happen is what I just mentioned, but you may have enough memory to load the mesh. Maybe you would have enough memory to run the plugin as well, but you just don't have enough memory to compute the connectivity information at first. And so that's where your plugin may crash because just your system doesn't have enough memory. The way that the TTK compact triangulation tried to solve that issue is to kind of bring that computation of the connectivity at the same level of your algorithm. So instead of in bulk computing all the connectivity information, it will try to follow the algorithm and jump around, loading just part of the connectivity information that you need in the mesh and run the algorithm at the same time. And all of that is supposed to be done for you without any extra effort. I'm not going into the detail of how this works. There will be a talk based by the main developer on this part on Thursday, so I'm not going to talk about this thing. This is a tutorial, so the goal here is to tell you how can you use it without knowing anything about the structure. So as a user, what do you need to know to use the compact triangulation rather than the standard data structure that is provided by TTK? Pretty much everything is connected to this scalar field here, called TTK Compact Triangulation Index. If your dataset has that scalar field associated with it, TTK will automatically decide if you want to run to use the compact triangulation rather than the standard explicit triangulation to run the plugin. So probably I should have started that video before, but this is just an example where you have a large simplicial mesh there, and on the top of the standard scalar field that you have associated with that mesh, you can also test visually if that scalar field is there by directly visualizing it. And so you see that there in the example, the scalar field is basically a bunch of blocks. That is what is being visualized there, which is what the compact triangulation used to implement that load and delete type of pipeline for the information. Another way that you can test to verify if you're using the compact triangulation or not is that it will be specified, of course, by your terminal. So in that case here, you have the explicit information that the compact triangulation is being used instead of the standard explicit triangulation. Now, a natural question at this point would be okay, dude, that's fine, but how do I define this scalar field for my data set that doesn't come with that scalar field provided? So the first method is the easiest, in my opinion, is that TTK now comes with a plugin dedicated for it, which is called TTK Triangulation Manager. So by using that plugin, you can decide if you want to define, basically create this scalar field index, and so automatically use the compact triangulation, or just go with the standard TTK explicit triangulation. But I can tell you already, will give you better time performance at the cost of eventually potentially run out of memory, as I just mentioned. An alternative way, if you want to play with the idea of having your own kind of clustering and segmentation defined, so to play around with that idea and potentially discovering new relationship between the clustering and the performance that that clustering can provide. Of course, you can define, maybe with a Python script outside of the TTK environment, your own scalar field. So you know, as long as that scalar field is provided with that name, the compact triangulation can be invoked. Awesome. So a few more details, still from a user perspective, if you want to play around with memory and with compact triangulation, what are your choices? The idea here at the developing stage was not just to provide yet another data structure with more compressed or better performances, was also providing the user the ability to kind of tune and play around a little bit with the performance. So one thing that you can do is that when you're using TTK Triangulation Manager to define this scalar field, you can play with a parameter that is called just threshold there, that basically will define the size of the blocks that are being generated by the plugin. And the idea is that the smaller your blocks are, the less memory you will use when the data structure will compute that connectivity information for that small block. if your like blocks are larger, so your threshold, which indicates like directly the size of your block, it may take a little bit more memory and eventually provide better time performance. At the same time, and again, like this will be explained much better from the developer's presentation on Thursday, you also have a parameter there that allows you to change the cache size. So that numbers there is just like a representation of how many of these blocks that are being pre-computed by the compact triangulation are also being saved in a cache so to be quickly reused. The idea is that the higher is that number, so suppose you use 1, it means that every block will be saved in memory after being pre-computed. That means a lot of memory, possibly like running out in the same problem that you had before, but like much better time performance. The smaller is that number, the fewer blocks you will be saving. That means that potentially the runtime will get much, much, much higher, but like if you have to get things done and you don't really care about how much time it will get, you can consider that option to compress and reduce the memory usage as much as you can. I would say like a few more comments about what do you need to know as a developer. So if you want to develop your own plugins for like this data structure, well, if you're already familiar with TTK, you know. If you're not, you don't have to know nothing. Of course, thanks of how TTK was designed, and here I'm not celebrating my work since I was not part of that design, every time that you include a new plugin, the plugin will be automatically supported by all the data structure that are there. So that means that when you are developing yourself, your own plugin, you will have automatically the freedom to switch the data structure that you want at no cost. Aside from that, I think like here is my email, and of course, if you have any question about the compact triangulation here, feel free to reach out to me either by email or in person during this week. And if there are any questions, and thank you very much.
Well, thank you very much, Federico. Maybe Florian, the next speaker, can get ready when we take questions. Is there any question for Federico? I guess all the scientific aspect of the work will be presented later this week about performances and benchmarks, I guess, right? But at least now you know how to use it. All right. Well, thank you very much, Federico. And now we'll switch to a presentation by Florian about the support of cinema in TTK and other cool things about the alignment of contour tree. Thank you, Florian.
Okay. So as Rino said, I will explain to you first how TTK supports cinema databases for the analysis of ensemble data, and then I will explain how the contour tree alignment module works. Okay, so what are cinema databases? They are simple file-based databases where each data product is a file with more data associated, so any property that you can think of, and the files can be in any format that you want. TTK provides an API for cinema databases, and especially we use this to represent ensemble data in the database and then provide the API to do all the heavy lifting for reading the ensemble, creating the ensemble, and also modifying the ensemble. Okay, so I will switch now already to the live presentation. Wait. Okay, so first let's have a look into how these databases actually look. So here we have a cinema database in the TTK data repository, the heated cylinder 2D, and as you can see, we have this data.csv file here, which contains just the file path. So this is basically constant for any cinema database. So we always have the path to the files for each data product. And then here specified in the header, you have a time value and a simulation value. So this is an ensemble of 23 simulations, and each with, I think it's 10 time steps from 3.5 to 4.5. But these properties, they can be anything that you want. They can, for example, if you use them for images, then they can be like a camera angle and a camera position or whatever. And if we go back to the file system, they are all stored in this data directory here, but this is not mandatory. And here we have VTI files for 2D scalar fields, but as I said before, they can be anything. So if we now go into ParaView, so we don't actually have to care about this file system because TTK actually does all the management for us. So we could read, for example, this database through the TTK Cinema reader, and now we have to choose the database path. And now this is read into a VTK table file. And as you can see here, so what we have is actually exactly the CSV file. So we have entries with the file path, then we have the simulation ID and the time value. And now we can use SQL statements to query this data. So we use the TTK Cinema query filter. And here we can put any SQL statement that we want. So for example, we can read out the ensemble member for simulation value 1 and time value 4.2. And now we have only one element in our VTK table here. And now when we actually want to read this VTI file, we can use the Cinema product reader. And now this is no longer a VTK table object, but actually a scalar field. Let's just quickly change to a color map here. And now we have this cylinder data set where we have like some hot area which rises from this cylinder down here. But actually this is not a single VTK object, it's actually a multi-block. So if we change the query from this very specific statement here to only specifying the simulation, then what we get is actually a VTK table which still has multiple entries. And then the multi-block that we get from the product reader also contains multiple VTK objects, which you can see here. And also TTK provides functionality to lay out these multi-blocks. And what we can see now is that we have this time series of scalar fields where this plume in the middle, it just rises higher and higher, and it gets then it separates into multiple parts. And because of the layout of this data set or this ensemble, we can not only query for a fixed simulation and then time varying time, but we can also use a fixed time point and then get very similar scalar fields for the different runs of the ensemble. Okay, so if we now want to apply some TDA on this ensemble, so for example, we want to compute the quantity tree, but let's first try to simplify these scalar fields, or let's skip the simplification as a first step, and then compute the contour tree with the FTM module. Then we can see that the contour trees are very noisy. We don't want that because it's very hard to extract meaningful information from it. So if we simplify this with a reasonable threshold, then we get much nicer contour trees for each of the ensemble members. And let's say we have a more complex data set, then we might not want to redo the simplification every time we do this, because it takes a long time. And therefore, we can use the Cinema writer, so we can write this intermediate step or cache it into a database and then use it for later analysis steps. So here we have to toggle this iterate multi-block flag. So otherwise, it was just write the multi-block as a single data object, but we want to write each member of the ensemble as a single data product. We have to specify a path. So let's just take the same as before and just replace the raw flag here with, let's say it's a simplified data set. And if we go to the console now, we can see that the data was wrote, and if we go to the file system, you can also observe this, that here's the simplified database with the data.csv file and the actual VTI files in the data directory. So if we now just read the simplified database, then we can do this contour tree computation just on the output of this simplified database. Okay, so now we'll switch to the contour tree alignment part, and it fits quite nicely because it makes heavy use of these multi-blocks and cinema databases. First, what are contour tree alignments? Or maybe first agenda, but let's skip this because the schedule changed a lot. So for ensemble of scalar fields, the idea of the contour tree alignment is that we want a contour tree, one contour tree that represents the topology of the whole data set. And we do this by computing the alignment of all the single contour trees. And this alignment is a super tree, so it contains actually each single contour tree as a subtree. And then on this super tree, we can lay out this, and then for each node or arc in the alignment tree, what we have, it represents a set of nodes or arcs from the original contour trees. So, for example, here, this one maximum in the middle here, it appears in all three trees, whereas this maximum on the left here, it only appears in 2 trees. And we can also visualize this. For example, in this image here, we chose to visualize this via the alpha value or the opacity. And then you can see that which features of the contour tree appear in a lot of members and which features appear only in a few of them. So, and how we do this in TTK. So basically, we want to use the same layout of cinema database that I've just shown you. And the reason for that is that the contour tree alignment filter, it can work for ensembles of multiple simulations, and it can also work for time series. It has basically 2 modes in which it can operate. And so basically, by only changing the query statement here for a fixed time point or a fixed simulation, we can also switch between the 2 modes for the input data. Okay. So we now choose the contour tree arcs here. This is a multi-block of contour trees where each contour tree is represented by a unstructured grid. The cells are just the edges of the graph, and the nodes are just the vertices of the graph. And here we can apply the contour tree alignment module or filter. And now this has a lot of options. So first we have to choose the scalar array, which represents the actual scalar values of the nodes, which by default from the upper of the FDM filter is named scalar. Then we have to choose the region size array for the cells, which is called region size usually. The segmentation IDs of the arcs in the contour trees. And the fourth option here is for another mode where we also attach the data of the actual segmentation, not only the IDs, but we will skip that for now. Then you can choose the two modes here, match over time or work on an ensemble of different simulations. And then we have a seed, and this is because the alignment algorithm is a randomized algorithm, so if you want to reproduce your results, you can choose a fixed seed here. Then we have multiple options for how we actually want to define similarity between the features of the contour tree. So we can use a purely combinatorial method. We can use arc properties like persistence or volume, and we can also use the scalar value. And how we weigh them is defined here. Here we can choose the arc property that we want to use. So this overlap option here is the one that then needs the actual segmentation, which we skipped before. And also how to, we can choose the average or the median value for the for the scalar values of the alignment nodes. Okay, so if we then apply this filter, does it work? So what you notice is that this is not actually a meaningful contour tree. It looks weird. And the reason is that there's no layout information attached. So let's clear this, and for time reasons, I will just show you how this then looks in the end. So here we have the contour tree alignment in the left view, and the frequency, so how many nodes are actually matched, is visualized on the nodes with a color map from blue to yellow. And then we have this, and on the arcs, we show the actual scalar value. And here we use the TTK planar graph layout to actually produce this layout. And then the contour tree nodes actually have like information about which regions are actually matched, or which arcs or nodes on the original trees are matched in them, in the segmentation IDs array and vertex IDs array. And in the right view here, we highlight in the ensemble which regions belong to the node that we chose on the left. So here we chose this main maximum, and as you can see, it corresponds to this main plume in the scalar fields. And we could, for example, also choose the this one here, apply the selection, and then what you can see here is that I want to zoom in, doesn't want to. So what you should see here is that these small maxima here around the cylinder are chosen, but for some reason I am unable to zoom in or out. I don't know. Let's pick then another node. It's again one we can't see. I'm sorry. Yeah, I don't know. Yeah, so actually you should see other regions here, but I can't zoom in, I don't know why. And one more thing, just to finish this talk. Parallel view is kind of limited in terms of interaction. So if you want to do further visualizations on this alignment, so for example, the fuzzy contour tree visualization from the paper we originally introduced this, then you can toggle this export alignment as JSON on here and give a path, and then it just writes the output alignment and the original contour trees as JSON files, and then you can use them for some JavaScript visualization or D3, whatever you want. Okay, so I hope that explained how to use the contour tree alignment module in cinema databases sufficiently, and I'm happy to answer any questions.
Well, thank you very much, Florian. Do you have any questions for Florian? I didn't see any question on Slido. If you do, please do not hesitate. Otherwise, everybody is going to be around throughout the week, so please don't hesitate to run into the speakers throughout the week. Do you have a question? So I will repeat the question for the remote attendees. So what do you gain from this ensemble view of the trees when there's a lot of variability in the data?
Yes, so the idea is that if you have features that appear in a lot of them, you can find them, and if there are features that are not, the alignment is not able to match them in a good way, then they are not matched, and then you have a lot of low frequency nodes, and then you can see like that there's not a high similarity, and if there are only high frequency nodes, then there's a high similarity. That's basically the idea.
I think that in ensemble simulations you might have like bifurcations, so two different settings that might come out of the simulation. So two groups of results, and each member is either one or the other, more or less.
Yeah, so then what would happen is that you have basically like a contour tree of nodes with frequency a half of the number of ensemble members if the alignment works well. I mean, the alignment algorithm can fail and then you only get gibberish, that's possible. But in an optimal setting, you just see a lot of nodes with half of the ensemble members' frequency. That's
all right. Well, thank you very much again, Florian. And now we will move on to the presentation by Jules about barycenters of diagrams.
Hello, I'm Jules. And so I will talk to you about distances, barycenters, and clusters of persistence diagrams and how you can compute those in TTK. So basically, given an ensemble of scalar fields, you are able to compute an ensemble of persistence diagrams, and then computing those distances, barycenters, and clusters enable you to perform some analysis tasks, such as comparing scalar fields, summarize the information about the topology inside the ensemble, and perform some clustering of the data. So basically, there are some metrics that are available on the space of the persistence diagrams. And one of them is the Wasserstein distance, originally from the field of optimal transportation. It's a nice metric because so it's computed as the cost of an optimal assignment between the features present in the two persistence diagrams. And it's nice because first it is stable on the space of persistence diagrams, and also it gives, well, an explicit mapping between the features. And what's nice in TTK is that we explicitly compute this assignment, so we get the explicit one-to-one mapping between the features of the data, so we can use that for visualization purpose. And note that the features in the data can actually be mapped to nothing, which corresponds to some kind of addition of destruction of a topological feature in the data. This assignment can be really costly to compute, so in TTK we use an approximate method, which is called the auction algorithm. And once you get distances, you can compute a barycenter. So a barycenter of a set of input persistence diagrams is some kind of average diagram that is representative of the topology of the whole ensemble. So it's defined as the minimizer of the sum of its distances, of the sum of the distances to each one of the input diagrams. And we can compute it using an iterative calculations. But this involves numerous assignment problems, which can be really costly to compute. So in TTK, we use a fast and progressive method. So in practice, the features of the data are progressively added into the computation. So what you get in the end is an interruptible algorithm. So basically, given an ensemble of persistence diagram, you can set a time constraint and get the best results possible within a time constraint. And I will demonstrate that. So this was for the computation of a barycenter, and we extended this approach to a generalization, which is a k-means clustering of an ensemble of persistence diagrams. Once again, the method is interruptible and progressive. There are two examples in the TTK data folder that you can play with, and it's about some data analysis of an Ensemble data set of a hurricane simulation, where you have 12 time steps that are classified into 3 clusters. So there are one example about the computation of distances between 2 members, and one about the clustering, k-means clustering performed on the whole ensemble. So I will just present a little demonstration. But first, you have to know that in TTK, those 3 operations, the computation of the distances, of the barycenters, and the clusters, is performed with one unique filter, which is called TTK persistence diagram clustering. And that is because the distance is a special case of a barycenter computation, and the barycenter computation is basically a special case of a clustering operation. And all you have to know is that this filter takes an input VTK multi-block dataset, so a collection of persistence diagrams. So let's jump to the live demonstration. So in the TTK data folder, I can just launch ParaView. And if you have already attended this tutorial the previous years, the only things that have changed is that now we use Cinema database in this example to deal with the data. So let's run the TTK Cinema Reader filter, and then we will fetch the database that contains this data set. And here you can see that we actually have 12 scalar fields with different time steps. And we have 4 at the beginning of the simulation, 4 at the middle, and 4 at the end of the simulation. We can then access the scalar field with the product reader. And here we can see that we have a collection of 12 scalar fields that are actually VTI scalar fields. Some kind of 3D image data, and we have 12 of them. And then we can just launch a computation of the persistence diagram directly on this multi-block, and it will actually create a multi-block of 12 persistence diagrams, one for each of the scalar fields. Let's run that. You can see the computation that iterates on each block. And here we have a VTK multi-block with 12 persistence diagrams. So I will just extract 2 of them in order to perform a distance computation. For that, I use the extract block filter. I'll choose the first one, the first one, and the last one. So here, there I have a multi-block with only 2 scalar fields. And then, once again, I use the persistence diagram clustering filter. And as is, if you only have two inputs, this filter will compute the Wasserstein distance between the two diagrams. For that, it uses, once again, the auction algorithm. So this is computing, right? So the Wasserstein distance is printed here in the console output of the filter, but you can also fetch it in the field data of the matching output here. And you can also, once again, you can visualize the mappings. For that, you have a little display option here for the matchings, and you can select inspect matchings, select some spacing, and here you can see the one-to-one mapping between the features of the two scalar fields, of the two persistence diagrams. So now, if we want to compute some clustering, I can just extract all blocks, or just get rid of the extract block, and then launch the same filter on the whole ensemble. And I will select a number of clusters. It's 3. And the important option is this one. It is basically the time constraint to run the algorithm, the clustering algorithm, or the barycenter algorithm. So here it is set to 1 second. I will put 0.1. And I will select the display method, cluster the stars to see a bit what's going on. Get rid of that. Right. So it's selected the wrong one. Yeah. Let's get rid of the matchings. So it was basically instantaneous, and we can see. Let me change a bit the colors. I will choose the cluster ID field to color the data. And here we can see the 3 clusters that were present in our data sets. These are the input diagrams, and at the centers are the centroids. So those are basically barycenter persistence diagrams that represent the topology inside of each ensemble. In particular, you can see that if I look at this cluster, the diagrams that are present in this cluster are visually similar, and the centroids is also similar, although it is different from this one. So now if I adjust the time constraint, also the result of the clustering is displayed in the console output, but it is also available as a field data on the cluster diagrams output. So here you get another field, which is basically the cluster ID. And then you can export this result as a new cinema database if you want to perform later things. So now you can adjust the progressive algorithm to set a different time constraint if you realize that you need more accuracy in the results. So let me zoom in on the centroid. And here, if I put 10 seconds, you will see that the computation takes a little bit more time, and what we see that basically more noise was added in the computation, but it didn't affect the general aspect of the centroid, and it certainly did not affect basically the classification of the classification outputted by our clustering algorithm. So that was it. If you have any questions, I'll be happy to answer.
I guess we can thank you. Do you have any questions? So if I may relate it to the previous question and previous talk, how do you handle variability in your data if you have sorts of regimes in your ensemble? Clustering features like those is one way where basically each cluster will describe each regime. All right. And now we'll switch on to Mathieu's presentation, which will be about merge trees and similar analysis.
Okay.
think it's it. This one, yeah?
Let me go.
Yeah, okay. Okay, that's better. So, hi everyone. My name is Mathieu Pont, and today I will show how to compute distances, barycenters, and clusters of mesh trees in TTK. So first, I will show what are mesh trees and one of their benefits over persistence diagrams with this simple example. So let's say we have two scalar fields in 2 dimensions here. We are shown in the third dimension the scalar values here. And we see that these two scalar fields are very similar. The only difference is that we have swapped the position of these two mountains, these two peaks of values. From these two scalar fields, we can compute the corresponding persistence diagrams. And we see in this example that the corresponding diagrams are identical, whereas the data are different. It is because the persistence diagram will inform us about the presence of the topological structure inside the data, but not how these structures are connected together in the scalar field. So this example shows a lack of discriminality of the persistence diagram, and to tackle this problem, we can use a more sophisticated topological abstraction that is called the mesh tree, and that will inform us, like the persistence diagram, about the presence of the topological structure inside data, but also how these structures are connected in the scalar field, giving here two different mesh trees allowing to discriminate the data. So in this tutorial, I will present briefly some methods that are proposed in the paper Wasserstein distances, geodesics, and barycenters of mesh trees, and how to use them in TTK and peer review. So in this paper, we propose a new distance between mesh trees, a new metric that we call the Wasserstein distance between mesh trees, because it is closely related to the Wasserstein distance between persistence diagram. So it is based on the edit distance, where we try to assign to each node of the first tree a node in the second tree. We can also destroy a node or insert a node. Each operation has a cost, and we want to find the assignment that has the global lowest total cost. And we can compute this using dynamic programming. So when we compute a distance, it will give us an assignment between the nodes of the trees, and this assignment can be used to compute a geodesic between these two trees that is a continuous transformation from one tree to another. Basically, it's just a linear interpolation of the assignment given by the distance. And we also use a normalization term, but I invite you to read the paper for the details. I will also say a few words about the relationship with the Wasserstein distance between persistence diagrams. But briefly, the idea is that we have a parameter that we call epsilon1 that allows to choose how much we want to take into account the structure of the trees in the computation. So when this parameter is set to its maximum value, 100%, the structure of the trees are not taken into account at all in the computation. And in this case, the R metric becomes equivalent to the Wasserstein distance between persistence diagrams. And more we decrease this parameter, more the structure of the trees are taken into account. And this parameter can be seen as a potentiometer that allows to choose a trade-off between the mesh trees and the persistence diagrams. So we also have been interested in the problem of a barycenter. So that means finding an average mesh tree of an ensemble of mesh trees, like the national average in statistics, but here for the mesh trees. Intuitively, it's a mesh tree that will be representative of the set because it will reveal us the global trends inside our data. Mathematically, it's the mesh tree that will minimize its distance to the set, and we also propose a method to compute that kind of mesh trees. And we can even extend the problem of the barycenter to the problem of clustering, where we haven't only one barycenter, but k barycenter, k being a parameter to choose by the user. And the idea of the clustering is that we want to create automatically groups inside the ensemble. We will create k groups, and and we also compute automatically the barycenter of each group at the same time. So in this example, we have 3 groups here. We have 4 trees in each groups, and we see the barycenter at the middle, at the center of each group that is automatically computed at the same time as the groups are created. So you have some example to how to use this method in TTK. You have some peer review state file in the TTK data GitHub and some Python script in the TTK website. And in this tutorial, I will show how to compute the clustering of an ensemble of scalar fields based only on their mesh trees. So I open peer review. Okay, and I will use also the Isabelle dataset, so the hurricane that moves over time, and I will use the cinema database of this dataset. So I call the cinema reader filter. Then I will go in TTK data and I'll choose the Isabelle.cdb folder, and I click on apply. So basically here is just, it will correspond only to the path to the scalar fields, but to load the scalar fields in a ParaView, we need to use the cinema product reader. I just check this option to keep the important information about the scalar fields. And here in output, we see that we have a multi-block dataset with 12 blocks that correspond to the 12 scalar fields of our ensemble. So we're going to visualize someone. I will extract the first one with the extract block filter. And in ParaView 5.10, we can do a volume rendering on a multi-block dataset. It's fixed in the 5.11, but here I will just need to convert it to an unstructured grid with the matchbox filter. And to have a fast volume rendering, I will convert it to an image with a resample to image filter and the dimension of the dataset. This step is just to have a fast volume rendering. So now I convert it to an image. I can do a volume rendering, and it appears instantly. So this dataset is a time series. Like I said, I will just change the color map. And it has 3 groups in this dataset. So this is an example of the first group, where we have the eye of the hurricane at the bottom of the scalar field. We can visualize now an example of the second group, where the eye of the hurricane is at the middle of the scalar field, and finally an example of the last group, where the eye of the hurricane is at the top left. So now the idea is that we want to do a clustering of this ensemble of scalar fields based only on the mesh trees. So I will use the FTM filter that allows to compute mesh trees. So I click on the cinema product reader that contains the 12 scalar fields, and I call the FTM filter. And I will choose the split trees that will capture the maximum critical points. In this data, it will correspond to areas where the wind velocity is high. So I use the split trees here. I click on apply, and basically when we apply a filter on a multi-block dataset and with some other conditions, but basically it will correspond to apply the filter to each block of the dataset. So this is kind of messy because the dataset has a lot of persistence pairs, but we'll see a better visualization just in a second. So we need to group all the output of the FTM filter with, for example, the TTK block aggregator filter to give that an input to the mesh reclustering filter. So the idea is that we need to have a format like this, a multi-block of multi-block, where each inner block is the output of the FTM filter. I will just use this moment to show a feature of the mesh tree clustering filter is that we can use both tree types at the same time. That means that a mesh tree can be either a split tree that will capture the maximum critical points, or a joint tree that captures the minimum critical points. We can choose either one or the other depending on the task or the dataset, but we can also use both at the same time. So here, I will show how to do that. I, again, call FTM filter by choosing the joint tree. Then I will aggregate all the output of the FTM filter with the TTK block aggregator filter. And now I will be able to call the mesh tree clustering filter and have a better understanding of what happens. So I select for the first input the split trees, for the second input the joint trees. I will ask to compute 3 clusters, and I will increase the persistent threshold to have the fast computation time. So now we have a visualization that we can configure to better see what happens. So first, I will not show the matching. I will decrease the space between the input trees. And now I will increase the space between the persistence pairs in the trees to better see what they look like. So here we see that we have 3 groups with 4 trees in each group, and we can color, for example, the input trees based on the original cluster ID. I will just change the background color to better see what happened. And basically what we see here is that we have the trees with the same color. That means the trees corresponding to scalar fields that are in the same group, they are automatically put together in the same group by our clustering algorithm. So we can find the original partition of an ensemble dataset by doing a clustering of the scalar fields based on the mesh trees. We can do a lot more with like aspecting the features inside the data, relating things like that, but I will not have the time to do that here. But I invite you to open the ParaView state file or see the paper. Before ending this tutorial, I would just say one more word, is that in TTK we have other distances between mesh trees. We have the edit distance of Schroeder-Murty et al. In perhaps few days, we have the branch mapping distance and the path mapping distance of Wetzel et al. And we have also the Wasserstein distance that I presented today. So if you have any question, I will be happy to try to answer them. And thank you very much.
Thank you very much, much, Mathieu, for this nice presentation. When Mathieu said hopefully in a few days, I will go back. So, basically, when I'm done reviewing, I will do that. But Florian's work will be available anytime soon. Do you have questions for Mathieu?
Yeah.
There's one question there. I will need to repeat the question in the microphone if you don't mind.
Yeah, so basically you're talking about the continuous constraint.
Yeah.
I'm wondering, is there an output from this constraint? Or
Is that what, sorry?
is there an output of this continuous constraint?
Is there an output?
Yeah.
Yeah, you have the clustering assignments, and you have also the visualization that I showed before, where you can inspect the clusters and the trees in each cluster to see, for example, which Scalar fields are put in which cluster. And you can also inspect the persistence pairs of the mesh trees to see what kind of features that looks like in the data, and you can and you can see what kind of features you should see in that kind of clusters. For example, the eye of the hurricane that is at the bottom, or things like that. Perhaps it's a fast answer, but I invite you to see the preview state file to better see something. I hope I answer your question.
And please don't hesitate to ask questions to Mathieu if you run into him.
Yeah, I can give you more detail after if you want to.
All right. I guess we can thank Mathieu again. So we were supposed to have one last presentation before I conclude, but we've been told that we are already beyond the end of the session. So I will conclude really quick. The talk that we're missing, though, is available on the page of the tutorial. So if you go to the page of the tutorial, you will see the pre-recorded version of the missing talk. And that talk is explaining how to derive some 2D planar layout visualizations of the ensemble. So how to see how things are, how the different trees or diagrams are related to each other. So to conclude, the take-home message that we wanted to give you is that if you have data that's defined on things that you can mesh, all the tools that we presented today can be employed, and TTK provides various features that ease this process. And it's particularly well adapted for ensemble data with the strategy of reducing the data to a topological descriptor and then doing the analysis based on the descriptors only. TTK is a software melting pot. We've got many other things, and this can also be a research platform. This is how we intended it in the first place. So it's like Federico mentioned earlier, it's very easy to create your new module. There's some scripts, and in 30 seconds, you can have your code that is running. And here, if you have a paper or an idea that you'd like to implement for your next paper, please consider trying to use this platform. There's a lot of features that we put in there to make your life easier. And if you want to contribute your new algorithm to TTK, this is also a process that we welcome, and we try to help people formatting the code such that it fits the standards that we have, and this is something that we've been doing in the past. And the advantage that you get is that your code is in TTK, and then it is supported and is maintained. It's also something, like Josh said, that you can use as a teaching platform, and this is also a showcase for our community towards potential users. So TTK needs you is going to be whatever you want to make out of it. So please consider using it, trying to test the software, contribute documentation if you want. Everybody can help, and everybody is, of course, very welcome. So with this, I'd like to just remind you guys about the dinner tonight, and that is pretty much it. And I would like to thank our sponsors. So thank you very much to the presenters, and thank you for attending this tutorial. And if you have any questions, please don't hesitate to come to us during the week. All right, thank you very much.